All right, recording's on, so feel free to start when you're ready.
All right, cool. Thanks guys for coming. Right, I know this is a bit of a weird day, but yep, last 2 weeks, right? So yeah, today I'll be talking about something called FEA, finite element analysis. You might have heard that term thrown around a few times. If you haven't, don't worry. I'll explain to you what exactly it is and what exactly is going on behind the scenes for this kind of analytical method. So what exactly is it? Essentially, it's a computational method just to numerically find internal forces, displacements, stresses, and strains for complicated problems that don't have any analytical solutions, right? So you can think about it we know what the stresses and the deflections and the strains are going to be in a cantilevered beam, right? So kind of what you see on the top right side. For that, it's a very simple loading condition. You have very simple geometry. And we know exactly how that's going to behave down to a T, right? We have no issues with that. But what happens when you try to do something that's a little bit more complicated, where you can't just use the equations that you learn in classes to kind of solve, right? And this is where FEA comes in. Essentially, we just kind of approximate this larger, more complex system as a bunch of smaller, more simple systems that we can solve for individually, right? So how does this work at the very basic, right? So essentially we break down a geometry with loads and constraints applied into smaller and smaller parts. We call these smaller and simpler elements, right? For which the analytical solutions are known. So for example, on the right, we see something that's called like a tetrahedral element, right? It just has 4 sides. And we know how this behaves like perfectly, right? So essentially, what the computer does is it just breaks down this complicated geometry into a bunch of smaller ones to just approximate it as closely as possible, right? So something to note is that in the terminology of FEA, the collection of all these elements in the whole model is called a mesh, right? And then the points that we actually want the computer to keep track of for the forces and displacements are called nodes, and those are just the individual corners of those elements, right? So where does it exactly do the math? And this is why I was kind of pointing out what nodes are, right? Essentially, in a static analysis, which is what we use on Inventor stress analysis tool for the most part, essentially like the forces at the nodes is a function of the nodal displacements and the stiffness of the element, right? And the stiffness matrix is directly derived from the elements, material, and properties and element geometries, right? So you can think about it like this, right? We know exactly how this kind of geometry is going to behave, right? Kind of like with cantilevered beams and all of that. And we know how our material is going to behave, right? So just like in those physics problems where you have a force applied to a spring and you then find the displacements, right? We can do the exact same thing over here. And this is just overly simplified, but honestly, like no matter how you look at it, this is how the computer does the math for FEA, okay? So kind of what I was mentioning before, like Inventor really only does static and modal analysis, as it's called. So as you noticed, like in the last slide, we just took care of like the external forces equals the stiffness of each element times the nodal displacements for each of the nodes in those elements, right? However, when you think of an actual physical system, you'll actually have like some inertial reactions, right? When you apply a force, it'll actually accelerate in most contexts, right? You'll also have the, I guess, damping effects. So essentially, like you can think of this, you know, in your basic physics classes when they tell you to ignore air resistance. Essentially, like this kind of portion of the equation takes care of that. So it's essentially anything that includes damping effects and is directly proportional to velocity. So in Inventor, right, when we use static analyses, we just completely ignore the inertial forces and the dampening forces, right? And we just assume that the external forces are going to be equal to the steady state, like what's it called, stresses and strains from our elements, right? Something that I'll point out is that other solvers do support dynamic analysis, but that's a lot more complicated, has its own issues, and fewer people in RoboJackets know how to use it. So this is kind of just like a tutorial and an understanding of how to use static analysis, since that's pretty much applicable to a lot of the stuff that we use. Like, for example, when we look at the force of the robot's body weight on individual components, we use static analysis just because it's not really accelerating. It's not really in any impact scenarios, and honestly, like, the damping effects are fairly negligible. So something that I'd like to point out, and this isn't something that we take a look at very often in RoboJackets, just because people aren't as specialized in this analytical toolbox, right? Since FEA is a numerical approximation, you have to be certain that errors from approximating that object don't stack up by seeing if the solution converges to a value after making the elements smaller, right? And what I mean by this is, like, you can think of this as like let's say I have a circle, right? So this is a glass with just quadratic elements. So you can imagine trying to fit squares to the entire geometry of this circle over here. It's going to be like an n-sided polygon, right? You can think of it like that. So unfortunately, because the geometry isn't exactly what the mesh is telling it, it's going to have errors from that, as well as from anything that's ignoring like higher order interactions, but we don't have to get into that. But essentially, like, whenever you're doing FEA in RoboJackets or in life or in work or whatever, you always want to make sure that your approximation errors aren't going to be significantly impacting your results. And kind of a rule of thumb that I personally use is that if your results, so like typically I look at like the stresses and forces going on inside the material, if there's a less than 5% change in results after doubling the element density, that's a reasonable sign that your mesh is converging and that you don't have to worry about the, what's it called? The approximation errors. Like, you can think about it like this. When you start increasing like the number of elements, right, to approximate it, that means your solution is going to be closer and closer at a certain point. But unfortunately, because you have so many elements, and when you increase the element density, you have a lot more equations and displacements and forces to take care of, right? It becomes more computationally expensive and takes longer to actually solve that problem when you actually like make it denser. So essentially, look at, you know, if the results are changing significantly when we refine the mesh. That's also to make sure that we're not wasting more time and energy into making sure that our results are accurate enough, right? Okay. The one thing that I like to point out, and this is something that we don't do very often, although in BattleBots, from what I remember, like most of the FEA that's used, right, even though a lot of those are impact scenarios, they use some very conservative estimates and typically use static analyses further from impacts, for example. They do have like test rigs for firing off the weapons, making sure that they don't break just under like regular use, so on and so forth. So the one recommendation I make is, if you have the time, energy, and resources, like, the one way to guarantee that a result is trustworthy, right, is to run a rigorous experiment with several trials and a good understanding of like what variables are controlled, and then compare the results of that experiment to what you see in the simulation. So like, like for example, if I were to do an FEA on the frame of the RoboNav robot, right, I can take a look at the strains and maybe measure some forces if I can at all, just to make sure that, you know, what we see in the analysis matches what we see in real life, right? And a big misconception that I'd like to point out, right? Whenever you hear people say, do the hand calcs, I will say that is a bit of an issue sometimes. It's helpful for when you want to know if your answer is in the ballpark occasionally, but it's not going to give you like good estimates. So what I mean by like, what's it called? Hand calculations is, let's say for the Mandy drum, right? The thing that I show over here. One assumption that you could make, that'd be kind of bad, but it's still something that you could do, right, to verify your results, is to consider like this portion that's sticking out as like a cantilevered beam, right? Then do the hand calc as if it were a cantilevered beam and see what the deflections and stresses are. But unfortunately, if the model is using the same assumptions that you developed the FEA model with, right? So if both of the assumptions you're making for that experiment or for that analysis are incorrect to start with, right, then that means that your hand calcs are going to be off, and then you're using that hand calculation to verify your FEA model. But since they're both wrong, you won't be able to tell just by hand calcs alone, if that makes sense, right? Your sources of error are going to be the same just because you're making the same assumptions, okay? So this is kind of an example I want to show just how to use this in Inventor. You guys can follow along if you want, but I highly recommend just taking a look at this on your own time, especially like with the what's it called, the lecture slides that are posted over here, like in the meeting chat, right? So I'm just going to run through how exactly to set stuff up in Inventor. Here I'm just going to do like a simple, what's it called, tensile test essentially. So we're going to be loading this bar with a hole in it with a force axially, and then seeing what the stresses and strains are, okay? So just create a part with these dimensions in Inventor, make the material aluminum 6061. This is important because whenever you assign the material for that part, it's also going to assign the material in FEA. Otherwise, you'll actually have to go into the software itself and make that correction, right? So the way you do it is just go into the environments tool, go to stress analysis, create study, and then press OK on the pop-up. And then, like I said before, if you didn't assign the material in the part level, you can actually assign it in the, what's it called, in the study itself. So once you create study and you're in this window over here, you can press assign and then change the material properties of each of your components, like over here, right? And this is important just because like it makes sense. Steel isn't going to behave the same as rubber, so you just want to make sure your material properties are as correct as possible, okay? Next time. The thing that I would like to highlight over here is this is like the bread and butter of FEA. Essentially, we refer to anything that constrains the system as a boundary condition, just borrowing the terminology from differential equations if you've taken a class in FEQ already, or if you've taken ME 2016. Like this is exactly the same, because essentially like what we're doing is solving a boundary value problem, but simplifying a little bit. Okay. The next thing that I'd like to say is like, since we're simulating a tensile test specimen with a stress concentration like the hole in the center, since there's charts that with experimentally determined values that we can use to validate the simulation, we're actually going to go over these calculations later on, okay? So what I want to point out with this is like, oh, nice. Oh, I was surprised Sam put the comment down. Okay, but nice. Yeah, this is exactly what's going on over here, right? A lot of what the solver's doing at the most basic level is applying the approximations and the numerical solutions that you learn in ME 2016 just in this kind of context, if that makes sense. But as I was saying, right, you can think of this as like an initial value or like something that you're doing to constrain the system. So for in this case, we're just going to be using a fixed constraint. That means that part isn't going to be moving whatsoever. So in any sort of, motion, you have 6 degrees of freedom. You'll have motion in the X, motion in the Y, and motion in the Z, and rotation about X, rotation about Y, and rotation about Z. Whenever you apply a fixed boundary condition, that's going to make sure that all of those are equal to 0, and that face isn't going to move whatsoever, okay? And the reason why we're doing this is just because the other side is going to have the forces that we're going to be applying, okay? So then afterwards, in the same exact like ribbon, you can press force, right? Just choose any load you want. You'll be able to see if you get the value right once we do the calculation and the mesh converges. Make sure that the load is in the same direction as shown on the right, okay? Just because we want this to be in tension, not compression. Whenever you start using compressive stresses on stuff, you have to be worried about a phenomenon known as buckling. But for this case, we're not going to worry about that. Like, we don't need to get into it. Okay. Then once you have all that set up, right, just press simulate, and it's going to create the stresses, the mesh for you. But you can change the mesh settings, like in this little box called mesh. I think the top right one is where you can say like what you want your elements, what's it called? Your element density to be. Okay. So after you click simulate and you get your results, you get these fancy, nice looking pictures, right? You want to make sure that this is all right from a numerical perspective and from an experimental perspective. So what we do over here is just click the top right box, like I said before, decrease the element size, right? And then just simulate it over and over again, okay? So one thing I will say is nothing will have changed if you just press OK on that mesh view or on the that mesh button that I told you on the top right. You're actually gonna have to regenerate it. So just you can either like double click the mesh button, the mesh under the, what's it called? I'm blanking on the name, but essentially on the left side where you have where you would usually see like features and parts and assemblies, right, in like a normal Inventor context. You can just double click where it says mesh on the left and you'll be all right, okay? So if anything hasn't been fully updated, like a red lightning bolt, this might have updated, they might have changed the icon from year to year, and this slide is 2 years old if I recall correctly. But essentially, like if you see like a lightning bolt or a symbol right next to there, that just means that's not updated and you can just, what's it called? Double click to make sure it's regenerated. And you can also, something that's helpful and you don't necessarily need to do is you can actually see the mesh by clicking mesh view just to verify that it changed, right? So like once you regenerate it and it becomes a lot more fine, that means you'll know you're doing all right. And that's pretty much it, okay? So the last step that I'd like to go over, right, is validation. Even though I said hand calcs are bad, for problems that are very simple and for which you have an understanding of what your assumptions are going to be doing to the system, it's still like a decent idea to make sure that you're close enough. But in this case, because there's like an experimental model of how this type of bar behaves, right? You'll see a lot of these curves like in a bunch of your like DefBods textbooks and machine design textbooks, for example. And this is what we can use to, what's it called? Verify our analysis. So from a couple of weeks ago, I think I told you guys about what stress and strain is. So stress, as we recall, just like in a tensile test, that would be the force being applied divided by the area. But in order to compensate for stress concentrations, right, as they're called, such as like the hole in the center, you usually like in a numerical context just multiply it by some, what's it called, constant K. And this is what this chart is used for. So depending on what geometry you're using, you can just multiply the stress that you're getting from there by that stress concentration factor, and that should give you your stress in this experiment. And over here, I'm just telling you like what force I used for the analysis, so then we can verify that the results from the FEA and the results from our calculations are spot on, if that makes sense. Okay? So after refining the mesh significantly, right, the simulation is actually over predicting the max stress a little bit. So like in our hand calcs that you can see on the top left, or on the top, we get 1773 PSI, right? And this is just because there might be some issues with like the boundary conditions or something that we're not characterizing correctly, or that the experiment that was used to characterize the, what's it called, the stress concentration factor isn't exactly accurate to what we're doing over here, okay? So don't take everything that you see like at face value. Always have some degree of skepticism when you're going into it, okay? So that being said, even though the max stress I said is over predicting, right? You'll actually notice that the max stress occurs at these fixed boundary condition, right? This suggests that our boundary conditions might not be accurate, so we might need to physically test this out and make sure that, you know, our analytical or our experimental data matches what we're doing analytically, okay? So then we can update our boundary conditions just to be a little bit more realistic. However, for this case specifically, right, and this is something that you might encounter, you can usually ignore what happens when you have the fixed constraint causing a huge stress concentration, right? Whenever an element or node is modeled as rigid, right, they have infinite stiffness. So remember from what I said before, like the governing equation behind this sort of problem is just F equals Kx, right? You can think of this fixed edge as having infinite stiffness because we're not getting any displacement. So you can notice that like if if it's not displacing at all and you're getting a huge stiffness, you're going to be getting a huge force. And because you're getting a huge force and you divide it by the area of like the element or whatever, right, you're going to be getting huge stresses. But that's not exactly right? This is just a consequence of how the computer's actually calculating these results, right? So you don't have to consider this in your mesh conversions and just probe for values in areas of interest instead. And if you guys want to learn more about what this problem exactly is called, just like look up singularity in FEA. It's not the same as the singularity in like AI. It's not as exciting, but you know, it's just something to look into if you want. So like I said before, you want to probe values instead. Essentially, like instead of looking at the max stresses over the entire part, I'm just looking at where the stress is concentrated in around the hole itself. And what we see is actually our results are a lot closer than what we saw a few slides back, right? This would be telling us that we're overestimating a crap ton, but instead we're only off by about 13%, and that could, again, just be a result of our boundary conditions being slightly off, all right? So the one last thing that I would like to say before I end this presentation is just like I said, for probing, you can actually look at what the stresses are in like each element or in each portion of the part itself by pressing what's it called, the probe button like on this ribbon over here, right? And you can also change what the maximum minimum stresses being displayed are, so like from blue to red, using these buttons on the right. Okay, this is just something I'll leave off to you to play around with, but essentially, that's it for FEA. We're going to be talking about controls in just a second. Do you guys have any questions, or have you guys been following along fairly well? Just feel free to ask right now, okay? Let me pop out.
Yeah, we're good in chat so far.
Okay, I'll be popping out the controls lecture in just a second. And Sean, if at any point I say something stupid, please correct me. But I think it should be fairly straightforward.
Yeah, it's kind of straightforward, honestly.
Okay, let me present this guy. Basic controls. All right, can you guys see what I have over here?
Yeah.
All right, perfect. Actually, give me 1 second. Let me put this to the left over here. Okay, so another thing that you might have heard, like people talk about in RoboJackets, is a concept known as controls. So this basically is just how we get one thing to go from one place to another, okay? So essentially, like, let's say you have a robot car, right? And you want this car to go from point A to point B. This might sound trivial, but like, how exactly do you do this, right? The robot is going to do exactly what you tell it to, so you have to be very specific with what you want. And just like, feel free to answer in the chat, right? This is something that I want you guys to, you know, cooperate with, or like, you know, engage with. That's the word, engage. All right, since it's a very general question, I might just go ahead and talk about the next slide. So, okay, sorry about that. So when you're moving a robot car, we want to go from like point A, and we want it to stop when it reaches point B. This means that the car is not going to have a constant velocity, right? And it will first need to accelerate as we want it to like speed up and gain some velocity as it moves forward, and then decelerate as it gets to the point of interest, right? And it may have a step with constant velocity between these two steps, so we're not accelerating whatsoever. Okay, and this is kind of what our graph of the, you know, position and accelerate, or the acceleration versus time is going to look like. So first you accelerate a little bit, right? You go at constant velocity, and then you hit the brakes as fast as you can when you're trying to get to point B, okay? Essentially, this is the basic questioning control. It's just how do we get things to go from one state to the next, all right? And when we take a look at the velocity versus time, this is pretty much what you're going to expect. So as you're accelerating, your velocity is going to be increasing, Once you stop accelerating, it's going to stay constant. Once you hit those brakes as hard as you can, it's going to, drop down to 0, okay? And you can think of this like, once we look at what the position looks like versus time, this is what you'll kind of get as a general idea, okay? So I did mention the word state before. What exactly do I mean by that? So the robot car forms a system, and this system can be represented with a state. So like just a bunch of variables, right? So you could call this position, velocity, acceleration. Yeah, pretty much like there could be a couple other stuff like voltages for like sensors and stuff, but you don't have to worry about that quite yet. But usually we don't need every variable in order to represent the state of the system. And in this case, we really only need the position and the velocity. So with the position data and the velocity data, you can have a complete representation of what's going on in this problem, right? Just because you can then take the derivative of the velocity to find some stuff, or the integral to get the position, stuff like that, okay? So in terminology for controls, the input is just the variable that we control. So right, with the car, we're controlling what the acceleration is, and the output is the variable that we want to observe, right? So we get the car from one position to another. The input is always going to be independent from the state variables. So if you apply an input to the velocity, then that input is not going to be the same thing as the state variable x dot, or the derivative of the position with respect to time. And the output is usually chosen among the state variables, and it could be just a combination of them. You need to be able to make sense of the output for your purpose, right? So like in the example that I just chose, like we want both the position to be at B, and we also wanted the velocity to be at 0 once we get to point B, if that makes sense, or at least from the example that I just gave, okay? And something that I'd like to describe is like how we actually implement these sorts of systems, and there's really two. So there's one thing called an open loop system that will just apply its input without having any knowledge about what's going on in the output. And then there's also something called a closed loop system. So this will factor the output into its input, and this is how the system checks to make sure that our desired output is reached, and this is what's known as feedback controlled, right? So an example of like an open loop system, for example, right, is just like, let's say you have like a dryer or a washer. You just apply those settings, you get it to go, and the machine is going to have no regards as to whether your clothes are clean or whether your clothes are dry. So because it's a stupid machine and it's not taking any feedback, there is some obvious issues, right? You've probably experienced this before. You've taken your clothes out of the dryer, and damn it, it's still moist. You got to put it in again and keep going, okay? However, in a closed loop system, right, if it's factoring out what the output is, so like in this case, if you have a really smart like dryer, it's going to be actually measuring what the what's it called? I don't even know what to measure there. I guess just like the humidity of the system, and just to make sure that the output is reached, right? So we have dry clothes in the end. And an example of a of a closed loop system that you see every day is like a temperature in a thermostat. You have a smart dryer, but the clothes still come out wet sometimes. Yeah, that sounds about right. Like everything that's smart isn't as smart as you would hope it to be, unfortunately. We do not live in the future quite well. People from 50 years ago wanted flying cars, bad dryers at this point. So not exactly the progress we want to see being made, okay? All right, so how exactly do we like represent this in kind of like a formal aspect, right? So in an open loop control, you have your desired output, you have your controller, and then that's going to be input to your system, and it's going to produce some output, okay? So in the example of the dryer, right, the controller is just going to be the knobs you turn, right? And then afterwards, like your system is going to be the dryness of the clothes, the rotation of the washer itself, stuff like that. So it's going to be modifying things about the system itself, but it's not getting any information about what's going on in between. But then in a closed loop control, right, you're measuring what's going on in the output, and then keeping that into consideration when you're actually inputting your desired output into the controller, okay? And this forms the fundamental crux of, of any control system, okay? And something that I'd like to talk about is just like, what exactly do we want to look for when we're talking about the control of dynamic systems? You can, in the example that I provided before, I just told you let's get from point A to point B, but there's a couple questions that we can ask ourselves. So the first of it is regulation. So for your, like, for example, you're forcing state X to equilibrium state, usually 0, with a desirable dynamic response, right? So with regulation, you can think of this as like, hold on, Sean, please correct me if I make a mistake here, because I think about about control a little bit differently. But essentially, this is like how fast we get to the output, and how accurate are we once we get to that desired position. The other one is tracking. So we can force the output of the system to track a given desired output with a desirable dynamic response. So essentially, once we have that output in a at that desired response, is it going to oscillate? Is it going to provide some errors, and so on and so forth? But essentially, like, what we want optimally is such that the speed, the stability, and the steady state error follow like some desired specifications. You can tell for like something to go from 0 to X in like X seconds. You can tell it to have an error of like plus or minus like some percent, and you can tell it to be stable within like a certain margin. So you make sure any oscillations aren't bigger than that margin, if that makes sense. So yeah, that's pretty much it. Now, what I'll quantify exactly is like whenever we talk about the inputs to a control system, we think of it in terms of error, right? So instead of just taking like the state variable like and it being input, we usually take the error as our input to our system, because that's going to control a couple of the parameters and a couple of the behavior for what we're telling the system to do afterwards, right? So in both of these cases, we're concerned with the difference between the current state and the desired state. So in a thermostat, like let's say you want your temperature to be 70, but it's currently 75, yours is going to be 5, okay? And that's essentially like, if you think about like in a thermostat, if you're, let's say 100 degrees over, you're going to want to change the thermostat, or you're going to want to change the heating of your system really quickly, right? It's going to be sweltering in there, okay? But okay, I'll get to the main point. There is a couple different ways that we can treat error that are going to be sensible. But so the main way that we control things, specifically in RoboJackets, I know there are more complicated forms of control out there, but they're not really covered in undergrad, and usually this suffices. You might have heard this before. It's called PID Control, and it consists of 3 different components. You'll have proportional control, integral, and differential control, and you can choose your appropriate like gains or the values that affect those components to achieve like a desirable dynamic response. But you don't necessarily need all 3. Like for example, people might use like PI control or PD control as because those are commonly used, and typically like the choice in like what you choose to include in your controller are going to have a massive effect in like, you know, how fast you're going to get to that point. Are there going to be oscillations? Are you going to have any steady state error, and so on and so forth? Okay. So when we talk about proportional control, right, essentially we're multiplying the error by a gain, so some constant. So the higher your error, the more input you want to apply, and the lower your error, the less input you will apply. And this is similar to like how a spring works, right? So whenever you push a spring forward, right, and you get it really far away from the equilibrium position, it's going to want to go back very, very quickly, right? But the closer you are to that equilibrium position, right, that spring that distance is going to be ever so slightly less, and your force is going to be a lot less as well, right? So the way that I would like to think about it as well is like in that example of the sweltering room that is 100 degrees hotter than you would like, right? Your heater and your air conditioning are going to want to operate much, much faster when the difference is 100 as opposed to when it's off by like 0.1 degrees, right? It would make no sense to have your heater like bounce up and down, trying to get that temperature as stable using like a constant gain with respect to error, if that makes sense. So the other thing that I'd like to talk about is the I component. So integral control. This is a little bit what's it called? A little bit less intuitive, but essentially you're taking account not just the error at your state, but the accumulated error from everything before and multiplies it by a gain. And this is kind of like predicting the future state and coming up with an appropriate response. And unfortunately, there's not really a physical equivalent for integral control, but it can be implemented like digitally, right? So we do have like the ability to, as we're, controlling like a robotic arm or a thermostat or whatever, you can always do those calculations, using your computer in order to do that, right? So the last thing that I'm going to talk about is differential control. So instead of taking into account like the difference or like the just the magnitude of the error or the accumulated error, this is kind of taking the rate of change of error into account instead or as well. And essentially, like when you're taking the derivative of the error with respect to time, right, you can think of this as like the faster your error is reaching zero, the harder the input is going to try to decelerate it. And this is a lot similar to how a damper works. So I think I mentioned before, like when we were talking about FEA, remember when we talk about air resistance, right? You can think about it like as you go faster, the air is going to push back a lot more and it's going to be slowing you down a lot more. But when you're going really slow, like if I'm just waving my hand here, I don't really feel a force whatsoever. So you can kind of think of that as your differential control as, as an element that's trying to stop your system from changing too rapidly, if that makes sense. Okay. And the last thing, you might be asking yourself, how exactly do we choose these games? Especially in like a lot of systems where it's not like you have an analytical solution as to how they behave, right? Typically, like we just set the integral and derivative gains to 0, and then increase the proportional gain until the output of the control loop oscillates at like a constant rate. And then once we have a desired P response, sorry, you can set some arbitrary value for the integral gain and just do some trial and error until those oscillations are reduced. And change this I value until the steady state error is reduced. But unfortunately, with integral control, whenever you increase your I value, you might overshoot your target a little bit too much, right? Just because it has that it's taking that previous error into account, even though what you have. I have PTSD from PID tuning. Understandable, honestly. So you kind of understand the problems with this stuff, but this is something that you'll definitely encounter even when you're working in RoboJackets, unfortunately. So like once you have like the P and I parameters, like I said before, you have that desired output using those two contributions like into consideration. You can then just start changing the D values until the system reacts quickly to its set point. And then something that's nice about the derivative gain is that it's going to decrease the overshoot of the controller response as well, right? So you're not going to get like massive jumps up and then jumps down. And this also lets it reduce the oscillations as well. Okay. And that being said, if you guys have any questions, like please throw it in chat before you forget, right? Because we're going to be doing a little review Kahoot that's a bit different than what we talked about today. This was kind of just for your own personal benefit, not necessarily for you to have a perfect understanding and be able to implement this in design. But once you like hear other electrical teams talk about PID tuning, or you have some senior mechanical members saying like, we did some stress analysis, like these are kind of what we're talking about. So like, I'll just give it a minute for you guys to, ask some questions in the chat. And you know what, since like it's independent, let me open up the Kahoot real quick. So you guys can join as you guys are asking questions, and yeah. And again, this Kahoot, like, don't worry about it. It's not what we just covered. It is just a review of the other stuff that we've done over the last 7 weeks at this point. So don't be too stressed out. This will be fun like always.
It's weird seeing a 7 number or 7-digit number. It's always like 6.
Oh, you're right. That is a little weird. I haven't noticed that yet.
There's a space between the 7 and the 9.
Also, Sean, is there anything that I missed with regards to control, or you think I covered that well
I think you did it pretty well. Yeah.
All right, appreciate it.
Yeah, that was good.
Is anyone else joining Kahoot? I think we've had these 4 people for a little bit.
Let's see here. We had a couple of people drop off. Wait, no, we just have one person drop off. So we only have 5 people.
Yeah. So I guess whoever is left, like, you might be AFK, so like I'll just wait for like another second. Otherwise, I'll just start in like a minute. I'm gonna get some water and I'll be right back. Honestly,
All right,
that might
sounds
be
good.
a good moment. All right. Honestly, I might just start the Kahoot now. I'm assuming someone is just AFK, if that's all right with you guys.
Sounds good.
So I guess you 4 are gonna be duking it out, just to make sure you're not the last one. But no worries. So let's just go ahead and start. So choose the correct order of operations in CAD for, yeah. Nice. All right. This is going to be an interesting one. I feel like you guys are very dedicated. You might get all these answers right. Let's go ahead.
Yeah, I'm expecting 100%.
No, I'm not going to say that necessarily. All right. Next question. After sketching a circle, what do you do to create a cylindrical feature? All right. Very nice. Okay. This will be down to whoever has the better internet connection, I guarantee you, unfortunately. All right, next question. What feature tool would you use to make this? Very nice, sweet. Okay, you guys are doing it. All right, let's see what's going on. Next question. True or false, the only way to make screw holes is by extruding a circle. Yep, you got that exactly correct. You can use the hole feature instead. Oh, this is a very fast-paced Kahoot game we're doing. Okay, next question. What is the purpose of project geometry? Yep, nicely done. It just allows access to entities outside of a sketch's scope. That's pretty much it. You might be able to use this to do complex shapes just because you can base your geometry off of what you've done previously, but this is directly what the function does in Inventor, okay? Next question. What feature tool would you use to remove material?
Ooh, this is an Inventor versus SolidWorks question.
Oh, it's just the
Extruded cut is
nomenclature.
not a thing.
Looks like 0.05.
Yeah, that's a
tough
trick
one. I'm
question.
sorry,
Yeah, that's a
guys. That
tough
was
one.
rough. I will say, who made this last one? Like, I've never heard this. I don't even know anyone
Yeah.
who's named Snyder, like last name. So
No, the Snyder cut is a reference to movie director.
Oh, Zack
Oh.
Snyder. Oh, God.
I don't know who you guys are talking about, so I'm just gonna move past it.
Okay.
I bet it was a misclick. Yeah. Let's see.
Ooh,
Next question.
yeah.
What feature in CAD is used to combine planes into a solid body? This is an advanced CAD question. What the heck?
Ooh, I need to change this again. I'm so sorry.
Stit.
All right, well, everyone got it wrong, so I guess guess that's okay. I need to make a note.
That's not even something you learned in 1770. I learned this in 4042.
Yeah, I didn't know
Alright.
this question.
All right, thankfully nobody got it right.
F in
So
the
you guys are all, yep, F in the chat. All right, next question. What is the best way to cat a sphere? Revolve a semicircle. Yeah, that works very well. Revolve a circle. You can do a revolve for a circle. I think it just takes a little bit. Honestly, this might not be a fair question because if you're thinking about it in terms of just like actions to do it, right? Revolving a circle would be faster.
Well, you
Because you don't
still
have to
need
draw
to
the
create a
line.
line.
Oh,
'Cause
you
have
do
to have
still
some
have to create.
axis. Yeah,
Okay, never mind. You're right about that. Okay, that's a tricky question.
that is a tricky one. I'm going to change these around.
You can do all of these though, so I think that was the purpose of it. Just do it in the least number of clicks possible. All right, next question.
Imagine
Oh, it's
filleting a
tight.
cube.
Imagine what?
Filleting a cube to get a.
Although, fun fact, now that we're talking about filleting cubes, it's actually possible to make a cube on a lathe.
Wow.
Yeah,
It's whack. It's doable.
Uh,
You shouldn't do it. You should probably just put it on the windmill, but still. All right, next question. I guess that's the opposite of filleting a cube. Purple means the sketch is defined. What the heck? Okay, false. Very nice. You guys have been using Inventor more than I have. I would.
Purple is undefined in this version. Black is defined.
All right, last question. True or false? In assemblies, you can constrain to the origin. True. That is.
We did go over that.
We
At least
did
it was in the CAD guide.
Yeah.
yeah, you do want to place your first part somewhere.
I'm actually thinking also, this would be radius of the shaft should be at the top.
Okay. So Jeff comes in third. Kirtik goes in second, and Paul.
All right. Second win for Paul. Oh, second win in a row.
Very nice, guys.
Yes, I am keeping track.
Well, that was pretty much it. Sorry about that. We'll fix these two. Well, this one's fine. We'll fix this question in the future, but that's pretty much it. Hope you guys enjoyed that Kahoot. There is one last thing. It is, in fact, guide time. So we'll just put the guide in the chat, and I'll go over it like really quickly, but you guys are free to stay or leave as much as you want, okay? So I'll pull that up. Yeah, so this is just going to be another example. Like, it's just going to involve a lot of different operations, but you already know most of it. However, this is going to be about drawing. Oh, never mind. This is drawings, not creating it. So you'll be given a part, and then you'll make the drawing for it. This is important just because, like, whenever you go ahead and machine stuff, it's really nice to print something out and just machine it by yourself based off the dimensions, not on like some post-it note like I've done in the past before. But however, if you go into industry, I'm pretty sure like if you hand a post-it note of dimensions to a machinist, they are not going to be happy. So this is why it's really important to know how to do drawings. Okay. Okay. So what do you keep in mind? Like what other parts are interacting with this part? What kind of interaction? Press, fit, bearing. So this is just like how we tolerance parts in general, and like what the reference point of the part is when you're actually machining it. Okay. What do you want from a drawing? You want it to be very clear, right? Clear locations for the data. Everything should be based from one single point. It should be simple, so like don't over dimension the drawing. Make sure it's robust and make sure it's complete, and that changes that in the CAD are not going to break it. All right. So you're just going to be going to this URL, downloading the part, and then making the drawing for it. And I'll quickly go over how to do that. Once you open the part and you import it, you go to File, press Drawing, and this is just going to open up another page. Okay. Your drawing is going to start blank, but then from this, you're going to have to start adding the different views and pretty much it. Okay. So the first thing that you want to do is just make sure that the sheet is of the right size, right? Because when you print it out on printer paper, if you have it in a 17 by like 11 sheet, which I think is like the default sometimes, it's not going to print out in your like average printer. You're going to want to change it to what's it called? Size D, I believe. Yeah. So this is or no, I was wrong. The opposite way around. Size A is the what you want. Size D is the default, which is too large. I think that's the 17 by 11 that I talked about. And other places might have other standards, so just keep that in mind. At this size, ANSI large is too big for a sheet. This is the, I believe the borders and the bottom right little, what's it called? I don't know what this is called. It's just like, it's what you put your name, the date, the engineering part, stuff like that, who signs off on it.
It's the title block.
The title block, that's what it's called. Yep, thank you. Is that at the title block? Oh yeah, it's literally on the next page. You just double click on the field text and then click on the clipboard item. From here, you can just edit a couple fields, right? So like part name, author, company, etc. Okay, and drop your part. Start selecting the drop your part like with the base feature over here, and start editing the measurements. And what the heck? Oh, I read that sentence completely wrong. To drop your part and start editing the measurements, select the base icon. Oh my god. You can then move your cursor to see other views of the base and then just click these to create other views, right? So you start with the top view and you get two side views over here, and this will give you a pop-up that'll allow you to define the scale and what kind of type of design for your part is going to be, like lines, transparent, solid, so on and so forth. Then what you want to start doing is just get to dimensioning. To get started, just go into the annotate tab and press the dimension button on the very left. Okay, and you can start clicking from one to the other. And once you place a dimension, double click it for a pop-up box. And it may happen automatically depending on like what settings you have, but you can elect to put different text in your dimensions under the text. You can also tolerance your part using this. So where it says like primary tolerance and if it's a symmetric tolerance, it'll just have one number, right? Depending on what like type of fit, so interference, sliding, transition, stuff like that, you'll have values that are going to be asymmetric. So you might have like a plus like 0.005 and then a minus 0.01. But generally, like you do symmetric tolerancing because that's what most parts typically need. You can also change like the significant figures by using like the the precision on the very right. That's useful just because you want to be able to, like if you're machining something, you want to be able to see the exact numbers like to the thousands sometimes. So yeah, definitely want to choose that. And when you're making holes that are threaded or tapped, they're going to have different, what's it called, like notation for it, right? So you can select the hole in thread and then select where on your part you want this to be denoted. And for these holes over here, it'll give you like automatically the thread type and pretty much it. Yeah. You'll also want to give the manufacturer, you guys can read this on your own, but essentially like there's a couple other things you can add to your holes, right? So you can give it a depth for how much you want to tap it, give it a depth for how far in you want the hole to go on, and so on and so forth. And essentially these values and symbols, once you click the appropriate boxes, will tell you like this is the diameter and this is like the depth. Okay, there's a couple others, like I think there's one for counterbore and countersink, but I don't know quite what the rest does, if I gotta be honest. But you know, that's GD&T for you. Yeah, this is pretty much just going on like where you start your dimensioning from, right? If you're going to be machining this using a mill, you're probably going to want to start it from just a right angle corner from the very bottom left or bottom right. It's just a convention. You don't need to stick with whatever corner you choose. You have to stick with like one corner you choose just to make it clean, but that's pretty much it. Now, yeah, this will just keep going in detail with what you want to do. And then finally, once you're finished with the drawing and you annotated all the dimensions you need, what's it called? You can export it to PDF and then print it out. So, yeah. And the last thing that I want to cover is just making DXFs. Oh, sorry, I should have clarified what GD&T is. But, wow, I feel like an old engineer already. So last thing, making DXFs. This is really useful for whenever you need to water jet or laser cut stuff, right? So what exactly is it? I think in lecture we covered this like a few weeks back. It's just a 2D file format that you can just export, and then a lot of machines will use to, start your cuts essentially. So in RoboJack, we primarily use it for the water jet, and it'll just cut all the lines on this 2D profile. So you have to be careful of what lines are on the part itself. So step 0, just make a new drawing, place the part. Oh yeah, when you're making a DXF, keep the scale at 1:1. Honestly, this is my least preferred method of making DXF files. Typically in Inventor, I use what we told you like the first time around, which is just right-click on a face and then click export to DXF like in your part file. But it's really up to you. This is just another way to do it if you want, okay? Yeah, this is definitely something Alex made. I love it. Alex is our president, by the way, just for referencing. He's a great guy. Yeah, this will just keep going over like what exactly you need to do at each step. And yeah, pretty much the rest is, delete your border, table, so on and so forth. And then finally just click save as once you've done all the stuff from before. And then save it as a DXF copy and then press finish. And that's pretty much it. Then you put it on a thumb drive and you bring it to the water jet and do some fancy machining and you got your part. Easy peasy. That's pretty much it. I did go really quickly, but I do want you guys to do this by yourselves, and follow along a little bit closely and actually do it. But we'll stay here for just a little bit more in case anyone else has any questions, but you're free to go whenever, okay? Thank you guys all so much for coming on this day. I understand why people wouldn't come, but hope this helped.